Okay, now we're going to tackle another optimization problem. This one is taken from Calculus 5th edition, Swakowski late trigonometric version, page 187. So it says, a steel storage tank for propane gas is to be constructed in the shape of a right circular cylinder, that just means what most people would call a circular cylinder, with a hemisphere at each end. The construction cost per square foot for the end pieces is twice that for the cylindrical pieces. If the desired capacity is 10 pi cubic feet, what dimensions will minimize the cost of construction? When I teach students to solve word problems, I like to use a system to help organize their thoughts. First is to identify the unknowns, in other words, what is the problem asking for. Next is to identify knowns, in other words, information given as part of the problem. And then you need to choose the formula or formulas that relate your unknowns to your knowns. Then you solve those formulas and do a little bit of checking, and you're done. So I'll go through this problem using this method. The unknowns are pretty easy to find in any problem. You look for the statements that are either commands or are questions. And so the question in this problem is, what dimensions will minimize the cost of construction? Now notice that they are asking for dimensions, that is more than one dimension. In other words, more than one specification for our tank. Well, if you look at a cylindrical tank with hemispherical ends, you can break it up into three shapes. There's going to be a hemisphere, there's going to be a cylinder. No, that's not quite right. All right. It's going to be a cylinder in the middle. And then there's going to be another hemisphere at the opposite end. Okay, pardon my mildly ugly drawings. Now realize that the horizontal portion up here on the cylinder has to be continuous with the curved portion over here. And the way you get that to happen is that both the cylinder and the sphere have the same radius. So there is only one radius for this entire shape. And so that constitutes one dimension. The other dimension is the length of this portion. Now, most cylinders, or at least in geometry, you typically draw a cylinder, kind of like that. And so this direction is your height. So we're going to call this, even though this cylinder is lying on its side, we're going to call the long dimension the height. And that's it. Spheres, or hemispheres for that matter, are determined entirely by the radius. So you only need one dimension for the two end caps, for the two hemispheres. So what we're trying to find is values of R and H that minimize the cost, which we'll abbreviate with a capital C. All right, what do you know? Well, aside from the shape, it says that the construction cost per square foot for the end pieces is twice that for the cylindrical piece. And one of the key terms here is per square foot. Whenever you see the word per, that implies a proportionality. In other words, if you have twice as much of one thing, you have twice as much of another thing. In this case, if we have twice as many square feet, we have twice as much cost. If we have 20 times as many square feet, we have 20 times as much cost. So what that means is that the cost is, it also says that the cost per square foot for the end pieces is twice that for the of the cylindrical pieces. So we're going to have two different costs cost functions, one for the end pieces and one for the cylindrical piece. So let's look at the cost of the cylinder is going to be some constant that's going to represent the cost per square foot times the area of that cylinder. And for the area of the cylinder, we're only going to use the walls. We are not going to use the end caps. Okay, so we do not use these sides of the cylinder in order to calculate the area. We also know that the cost of the hemispherical portions is still going to be a function of area, and it's still going to include that K, but it's going to be two times K. And this probably reflects the fact that it's harder to fabricate a sphere than it is to fabricate a cylinder. Cylinder, you can just take a sheet and then roll it around some sort of what's called a mandrel, something to hold it open while you bolt it in place. Spheres, you basically have to custom make them. All right, moving on. The last bit of information it tells you is that the desired capacity is 10 cubic feet. Okay, capacity, that's the same thing as volume. So we know that the volume, no, not 10 cubic feet, 10 pi cubic feet. So we know that our volume is 10 times pi cubic feet. Okay, what formulas do we know? And I'm even going to do a little bit of substituting in the formulas. The barrier between setting up formulas and solving formulas is kind of vague. Well, we know that the total cost is going to be the cost of the cylinder plus the cost, 2 times the cost of the hemispheres. The two hemispheres are identical. Now, if you look at two hemispheres constitute one full sphere. So you could just call this the cost is equal to the cost of the cylinder plus the cost of one spherical portion that just happens to be cut into two hemispheres. And if we substitute these equations into there and there, then you will end up with that the cost is equal to K times the area of the cylinder plus 2 times K times the area of a sphere, or if you want, you could say 4 times K times the area of a hemisphere. Either way, it's fine. However, if you look up areas, you'll usually find areas for spheres, but you won't find areas for hemispheres. So this works easier based on our table of a table of knowns. I don't expect you to memorize some of the more esoteric area formulas like area of a sphere. So looking up the area of the outer, again, the wall of a cylinder, this portion, not that part, the area of a cylinder is going to be 2 times pi times r times h. And the area of a sphere is going to be 4 pi r squared. All right, do a little bit of cleanup work here. Cost is equal to 2 times k times pi times r times h plus 8 times k times pi times r squared. All right, we have a problem here. This is definitely progress, but we still have a bit of a problem. And that problem is that we currently have two variables in our cost equation. One of them is r and the other one is h. Whenever you have an equation, you want to make sure it's down to one variable. Otherwise, you need more equations. Now, fortunately, we are given some information that we haven't used yet, and that's this volume function here. Volume is 10 pi, and we can use that to relate R to H. Volume is a function of R, and it is a function of H. So if we play our cards right, we can relate volume. We can use volume to relate R to H, and then substitute all of that back into this equation here. All right, let's go to the next page and work on that. Like I said, you can consider this to be, or this storage tank to be, one hemisphere, one cylinder, and another hemisphere. These are admittedly ugly shapes, but, or you could consider, could put the two hemispheres together and get one full sphere. Regardless, the volume has to be 10 pi, and so that's going to be the volume of a sphere plus the volume of a cylinder, which shares the same radius. So, looking up our volume formulas, the volume of a sphere is 4/3 pi r cubed. Volume of a cylinder is pi r squared times h. And the first thing you can do with this equation is you can cancel out the pi's. Now, remember, the whole point of having this equation is so that we can substitute it back into the cost equation and eliminate a variable. So it really doesn't matter which variable we eliminate, R or H. So let's just look at this equation and figure out which variable is easier to isolate. Well, R shows up in two different places with a different exponent. So isolating R, getting R on one side and known quantities in H on the other side of this equation is going to be pretty difficult. So instead, let's try isolating H. So if we subtract the 4/3 part of the equation over, we'll get 10 minus 4/3 r cubed equals r squared times h. Divide both sides by r squared. That's going to give us 10 over r squared minus 4 over 3r, 4r over 3 is equal to h. All right, this is good. We got h's on one side and known quantities in r on the other side. That means we can take this equation and substitute it into the other cost equation. I'm running out of room here, so I'm going to recopy the cost equation onto the next slide and then continue from there. Okay, so we've recopied the cost equation here, and now we need to take this equation for h and look for the h's in the cost equation. There's only one of them. It occurs right there. So we'll take out that h and replace it with this statement for r. Alright, so combining the equations now, we get cost is equal to 2k pi times r times the quantity 10 over r squared minus 4r over 3 plus, and there's no h's in this second term, so we'll just copy it down, 8k pi r squared, and that's kind of an ugly pi. Let's see, there we go. All right. That's a 2. Wow. It's really. Okay. while looks like a complicated equation, it is a solvable equation because we've reduced it down to one variable. So let's keep working here to expand this out algebraically, and then we'll take, remember the whole point is to optimize this for lowest cost, and so we'll have to take the derivative, find the critical points, and make sure that those critical points are in fact in a minimum. So cost is equal to 2 times k times pi times the quantity 10 over r minus 2 times k times pi times the quantity 4r squared over 3 plus 8 times k times pi times r squared. Alright, keeping up with the cleanup here, so this is going to give us 20 times k times pi times r to the negative first power plus, no, not plus, minus 2 thirds, not 2 thirds, 8 thirds times k pi r squared plus 8k pi r, I'm running out of space here, r plus 8k pi r squared. And so combining the two r squared terms, we get that the cost is equal to 20 times k times pi times r to the negative first minus, let's see, 8 is 24 thirds, 24 thirds minus 8 is plus 16 thirds k pi r squared. Okay, now we can take the derivative of this. This is going to be dc dr is going to be 20 pi negative 20 k pi r to the negative second plus, let's say taking the derivative here, we get 32 thirds k pi r. Alright, now we set the derivative equal to 0. Negative 20k pi, and let's call this pi over r squared, plus 32k pi r over 3. Alright, so the first thing you should notice is that the k's and pi's show up in both terms, so we can cancel that out. Basically divide through everything by k pi, and since we've got a 0 over here, doesn't matter what we multiply or divide through, it's not going to change the 0. Also, both 20 and 32 are divisible by 4, so this breaks down into negative 5, and that breaks down into, let's see, 32 divided by 4, that's 8. Alright, so now we have a formula that shouldn't be too bad. Let's move to the next slide, though, to give ourselves some space. Okay, there's our new formula, and if we multiply everything through by 3r squared, we still have a 0 on this side, and this will give us negative 15 plus 8r cubed. Okay, now it's just a little bit of simple algebra. Add the 15 over to this side, divide both sides by 8, and take the cubic root of both sides. And remember, cubic roots can be negative, so you don't have to take into account the plus or minus. Alright, so this is our value for R. If you want to express this in decimal quantities, which is useful for if you're actually going to build the thing, you just bust out the calculator. Give me a moment. That would be 1.23 cubic feet. Sorry, not cubic feet. Radius is length, so it's just regular feet. And remember, our unknowns were the values of R and H, so we have to also find the value for H. Let's find the simplest equation that relates R to H, and it happens to be this one right here, which I'll recopy onto the next page. By the way, one thing I should note is that you could also rewrite R as 1/2 times the cubic root of 15. Because 8 is 2 cubed. But anyway, getting back to our value of H, if we substitute these values, the 1/2 times the cubic root of 15, in here we get 10 divided by cubic root of 15 thirds squared minus 4 times the cubic root of 15 thirds over 3 is equal to H. And granted, this is a bit of an ugly equation, but it's all numbers. So one option is to just throw it all into your calculator. The other option is to actually try to work this out analytically a little bit. Wait a minute, it's not 15 thirds, it's 15 eighths. So I need to change that to an 8 and that to an 8 as well. Okay. So let's see, factoring out the 1/8 and then squaring it, that's going to be the same thing as 10 over 1/4 times the cubic root of 15 minus, and then doing the same thing up here, that's going to be 2 times the cubic root of 15 over 3 is equal to H. And let's see, simplify the compound fraction over here. So we got 40 over the cubic root of 15 minus 2/3 times the cubic root of 15 is equal to H. And if we, let's see, if we multiply the top and bottom of this first term by the cubic root of 15 squared, let's see, that will give us 40 times the cubic root of 15 squared, which is 225, I think. Yeah, 225 divided by 15 minus 2/3 times the cubic root of 15 is equal to H. Not sure how much further we can do, we can work with this that would still be productive. The 40 and the 15 break down into an 8 and a 3. Sorry, I made a mistake. Way back up here, when I squared stuff, I forgot to apply the squaring to everything down here. So I actually need to kind of start over on about a quarter of this slide. on a substantial, not quite a quarter of the slide, but a substantial portion of the slide. So that goes away, that goes away, that goes away. All my work over here is probably still good. So let's try this again. 10, factor out the 1/2 and square it, so that gives us 1/4. And then we still got the cubic root of 15, but it's 15 squared. Okay, so this again simplifies to 40 over the cubic root of 15 squared. Multiply top and bottom by the cubic root of 15, you get 40 times the cubic root of 15 divided by the cubic root of 15 cubed. And then this becomes 40 over 15. 40 over 15 is 8 over 3, so that's 8 over 3 times the cubic root of 15 minus 2 over 3 times the cubic root, cubic root of 15 is equal to h. And so last but not least, we find that we get 6/3, or 2 times the cubic root of 15 is equal to h. So 2 times the cubic root of 15 equals h. Or, again, if you actually have to build this thing, you're going to say 4.93 feet. All right, so our answers are a height, or if you prefer, length of the cylindrical section is 4.93 feet. The radius of the entire device is 1.23 feet. I almost forgot to do one thing, which is to check to make sure that the r is equal to 1.23 feet really is a minimum. And if you'll remember, a minima are one of two things. Either it's a critical point where your derivative goes from negative to positive, in other words, you go from decreasing to increasing, or it's what your endpoints. And for this problem, our realistic endpoints are r equals 0 and r equals infinity. However, as I discussed before, r equals 0 is not a realistic endpoint, is not really a realistic endpoint, it's a limit. We can have very low r's, but we can't have 0r. Now, if we look at the function for cost, or rather the derivative of cost, it looks something like this. Now, looking at the endpoints, let's take the endpoint first, because that's kind of easy to work through. At an endpoint, if r equals infinity, then that means that this part of the equation goes to 0, and this part goes to positive infinity. So, so this is not actually, wow, I'm screwing this up. Sorry, you shouldn't plug r equals infinity into the derivative, you should plug it back into the main function. So let's check on either side of our critical point of 1.23 feet. Let's try r equals 1 and r equals 2. Those straddle 1.23 feet, and there's no other critical point, so we don't need to worry about going past another critical point. So in this stage, dc dr is going to be negative 20 k pi over 1 squared, which is just 1, over minus 32 k pi pi over 3 times 1 squared, which is 1. And remember that k is a positive constant, so we're going to factor this out. And so this is going to be k times pi times the quantity negative 20 minus 32 over 3. And while you don't have to exactly work that out, since these two parts are, that's positive, and this whole thing is going to be negative. All right, we have a, that should be a plus sign right there. We have negative 20 plus something that is substantially less than 20. That means that this is going to be a negative number. So, looking okay so far. We start with a negative. Now we have to make sure that when we go past r equals 1.23, we start getting a positive. So let's look at r equals 2. So in that case, dc dr is going to be negative 20k pi over r squared, which is going to be 4, plus oh, whoops, made a mistake. That shouldn't be an r squared. Doesn't affect our r equals 1 because 1 and 1 squared have the same value, but it does affect this. So we're looking at 32 times k times pi times 2 divided by 3. Factoring out as much as we can, this is going to be 4k pi times the quantity 5 over 4 times negative 5 over 4 plus 16 over 3, and this is going to turn out to be a positive number. Okay, so r equals 1.23 is a local, is a minimum. Now we also need to take r equals infinity and plug it back into the cost equation, which is located, probably the most concise version of the cost equation is right here. I'll recopy that onto the current active slide. Oops, went too far. Okay, let's look at how this function is affected by r equaling infinity. Well, if you look at this term, that's r to the negative first, and so that anything, infinity to the negative first power makes this whole term 0. Infinity to the negative first power is 0. And then this whole term, because it's got an r squared, is going to become a positive infinity. So as r approaches infinity, c approaches infinity as well. So r equals infinity is not going to be a minimum. So we are left with our only answer being r equals 1.23 feet and h equaling, refresh my memory, 4.93 feet.